In the vast expanse of space, a curious phenomenon unfolds, where mass seems to diminish due to the delicate interplay of vacuum fields. These fields, imbued with negativity, arise from the positively charged matter of celestial bodies, stars, planets, and galaxies. As they interact, they create a unique environment where space itself becomes a stage of repulsion, much like two magnets that cannot coexist in close quarters. This cosmic dance establishes what can be described as a universal negative field that influences the movement of everything within it. Imagine a ship navigating under the influence of this dark root, a term that encapsulates the zero-point polarity of the vacuum. In this intriguing state, the ship achieves zero mass, transcending the usual confines of inertia and evading the constrictions of time dilation. This notion aligns with what could be termed a zero-point vacuum warp system, a departure from the traditional understanding of spacetime curvature as posited by general relativity. As our universe ages, positively decaying matter, such as dying stars and fading galaxies, contributes energy to this negative vacuum field. This energy transfer is crucial, as it feeds into the ongoing expansion of the universe and serves as the essence behind the Hubble anomaly. Contrary to the contemporary interpretation that attributes this expansion to dark energy, it is the interaction between matter decay and the vacuum field that truly drives the cosmos to grow. The critique of Einstein's theory of relativity emerges from this discourse, shining light on the paradox of gravitational physics. Relativity establishes a speed limit dictated by the speed of light, yet simultaneously employs space curvature as a means of generating gravitational forces. This leads to a conflict. Space cannot be both a passive stage limited by speed and an active participant in producing gravitational effects. This contradiction calls into question the very nature of our understanding of space and motion. Delving deeper into the implications of these theories, quantum physics posits a new framework that introduces net motion values and a conception of weightlessness applicable to all forms of matter, even celestial bodies like stars and planets. In this view, the assumption of infinite mass at the speed of light is redefined. Instead, we embrace the concept of adaptive masslessness within the structures of a vacuum, challenging the classical perspective that has prevailed for centuries. One of the most thought-provoking aspects of this exploration is the fate of celestial energy. Over time, as organic life forms and heavenly bodies age and use energy in their myriad activities, a compelling question arises: where does this energy flow? The answer suggests a dynamic interplay. This energy is absorbed by the vacuum field, transforming into the very fabric that causes the universe to expand. The vacuum acts as a cosmic capacitor, storing and redistributing energy in a manner that fuels growth and decay simultaneously. To encapsulate these intricate ideas mathematically, we can consider a basic relation that describes how the vacuum relates to the energy of celestial systems. E_vacuum equals the plus/dt. dt signifies the net decay energy from positive celestial entities, with the negative sign reflecting the energy absorbed by the vacuum field. This relationship extends to the rate of universal expansion, creating a bridge between energy states and volume growth, as expressed by the equation dV_U/dt equals beta middle dot E_vacuum, which links the expansion of the universe to the density and polarity of the vacuum. Philosophically, we arrive at a provocative conclusion: space is not a neutral backdrop to celestial events, but rather a dynamic field shaped by the energies and interactions of the positive systems it contains. This perspective inverts Einstein's assumption of a neutral vacuum and instead posits that the vacuum is a reactive polarity field. This has far-reaching implications for propulsion, aging, inertia, and the very essence of universal expansion. In this ongoing quest for understanding our universe, as we grapple with the intersections of vacuum fields, quantum physics, and classical theories, we find ourselves at the precipice of a new paradigm. A paradigm that challenges established notions and beckons us to explore the unknown realms of space, time, and energy, a journey fueled by curiosity and the ceaseless quest for knowledge. The physics of spacetime, as described by Einstein's theory of general relativity, reveals the complex interplay between matter, energy density, and gravitational force. Einstein's field equations demonstrate how mass and energy warp spacetime, creating gravitational fields. This warping allows for concepts that challenge our understanding of motion and the cosmic speed limit, ultimately questioning the speed of light's role in the universe. In the realm of quantum mechanics, zero-point energy fluctuations can theoretically generate negative energy density, which could create negative torsion in spacetime. Such a combination of relativistic and quantum principles could lead to breakthroughs in our perception of motion and speed limits. In 1994, Miguel Alcubierre proposed a warp drive, a theoretical concept enabling spacecraft to achieve near and even faster than light speeds by warping spacetime. Alcubierre's idea involves a bubble of warped spacetime, wherein a ship could move within distorted space, creating an effect akin to surfing on a wave. The existence of a warp field remains a subject of inquiry, notably whether it could manifest on a macroscopic scale and remain stable long enough to observe measurable effects. The possibility of such warp fields brings forth questions about their technological realization and the conditions under which matter allows for negative energy density. Rodney Kavetsky's work re-examines traditional gravitational theories, identifying flaws in Newton's and Einstein's frameworks. Kavetsky emphasizes the invariant speed of light as a barrier established by Einstein over a century ago. This led to a revolution in understanding the universe, sparked by observations that still challenge conventional theories. Notable phenomena include the relationship between redshift and angular size, the number of distant bright objects that contradict standard geometry, and the realization that the expansion of the universe appears to accelerate. Despite ongoing advancements in physics, gravity remains ununified with other forces, leaving questions about its origin and effects unaddressed. In 1948, Hendrik Casimir and Dirk Polder proposed the existence of negative pressure due to quantum vacuum fluctuations. Their theory demonstrated that uncharged metallic plates, when placed closely together in a vacuum, experience an attractive force due to differential energy densities. Though not immediately conclusive, these ideas laid the groundwork for understanding the Casimir effect, where the interaction of virtual particles results in observable forces. Direct experimentation, such as Steve Lamoureux's work in 1997, quantitatively assessed the Casimir effect, validating earlier theories and hinting at the potential for quantum research to uncover deeper understandings of spacetime manipulation. As scientists continue to probe the boundaries of physics, studies on the Casimir effect may further elucidate the characteristics of negative energy density and its applications on nanoscale technologies, impacting fields like quantum circuitry. In the discourse surrounding warp drives, we find a reference to Alcubierre's hypothesis that viewing space as an expanding entity could prompt a reassessment of speed limits. According to Hubble's theory, as space expands, the speed at which it does so may exceed even light speed. This perspective posits that a vessel traveling near light speed could still take advantage of the expansion of space itself. The ship's motion does not necessarily imply it accelerates beyond light speed, but rather that the fabric of space underneath it shifts, supporting a different understanding of motion. These theoretical constructs challenge conventional views, paving the way for innovative experimentation that could one day yield practical applications of warp technology. The challenge remains whether the necessary physical conditions for stable warp fields exist, as predictions from quantum and relativistic physics continue to intersect. Each new discovery might bring humanity closer to navigating the cosmos in ways once deemed impossible, promising a future where the cosmic speed limit may no longer bind us. The ongoing quest for knowledge is fueled by the mysteries of spacetime and the exhilarating prospect of traveling among the stars, unlocking the secrets of our universe.
In the realm of physics, the pursuit of faster-than-light travel often invites analogies that oversimplify complex theories. One such analogy is the notion of punching a hole in spacetime, an idea popularized in various discussions about superluminal motion. However, this imagery misrepresents the essence of general relativity. According to Einstein, spacetime curvature is not merely a consequence of speed, but rather a function of energy and mass density. Simply put, moving quickly through empty space does not warp spacetime, it is mass that exerts this influence. While a fast-moving ship may possess an increased relativistic energy when observed from a different frame of reference, it does not create a gravity well or manipulate spacetime as one might imagine. The analogy of tearing or puncturing spacetime, though visually compelling, falls short of scientific accuracy. Spacetime is not a fabric that can be ripped, rather, it is a complex structure that requires colossal forces, like those found in a galaxy, to alter significantly. As one approaches light speed, more energy is needed for acceleration, diverging towards infinity, but never allowing one to exceed this cosmic speed limit. The real breakthrough in our understanding lies in concepts such as those proposed by Miguel Alcubierre, which suggest manipulating spacetime itself, contracting in front and expanding behind a spacecraft. This approach retains the ship's local movement below light speed while allowing the spacetime around it to facilitate faster-than-light travel. Thus, acceleration is not merely about speed but involves intricate interactions with the spacetime metric. Quantum physics deviates further by proposing a model where propulsion energy acts independently of spacetime curvature. Here, propulsion is viewed as momentum exchange with a space field rather than traditional methods that warp spacetime. The energy expended through propulsion, transferred via exhaust, does not accumulate around the spacecraft to create notable curvature. Instead, it illustrates motion without significant alteration to the underlying spacetime metric. In this framework, local motion is decoupled from the geometry of spacetime. Expanding space can create superluminal effects in coordinate systems. Yet local observers will always adhere to light speed limits. The typical framework posits three components: local motion, metric expansion, and curvature, each operating independently, thus clarifying how propulsion can occur without altering the cosmic structures at play. By embracing these ideas, we can envision a theoretical pathway towards efficient space travel that aligns with the known laws of physics, while still exploring the boundaries of current understanding.
In the advanced Kavetsky model, propulsion energy utilized for thrust is expelled through the exhaust, allowing the ship to gain momentum and speed, but not mass. This process does not warp spacetime significantly. Quantum physics aligns with established physics principles, demonstrating that a rocket accelerating by expelling reaction mass does not bend spacetime merely because it generates thrust. Instead, quantum physics conceptualizes propulsion as a momentum exchange with a spacefield medium, permitting acceleration without the distortion of spacetime. This distinction sets the model apart from traditional warp drive theories, such as those based on Alcubierre metrics, while maintaining coherent logic. A compelling summary from the paper articulates this concept elegantly. In quantum physics, propulsion energy is expended as thrust and carried away in exhaust, producing ship acceleration without inducing spacetime curvature. Speed arises from momentum exchange with the spacefield, not from warping the metric. This innovative perspective essentially reverse engineers a variant of unified field theory. If we envision space as a grid comprised of particles like Higgs bosons that generate mass, then propulsion can be understood as the mechanical manipulation of that grid. This manipulation effectively reduces the resistance encountered in front of the vessel. By understanding propulsion in this manner, we gain insight into the mechanics of acceleration without the need for conventional notions of spacetime manipulation. This clarity allows for new explorations into propulsion technology, firmly rooting the ideas in both theoretical physics and potential applications, leading to a more profound comprehension of how spacecraft might navigate the vastness of the universe.